Hello everyone, Oleg is here. Welcome back to our calculus series. In the previous videos we introduced the concept of a function and function classification. Today we'll be discussing sequences, particularly numerical sequences, which are foundational in calculus and will be essential for understanding limits and series. We'll start with the idea or the concept of a sequence. In mathematics, a sequence is an ordered collection of elements, where each element has a specific position or index. Order is essential as it defines the structure of the sequence, and this structure means that the same element can appear multiple times in different positions. So what these elements may be? These elements may be actually everything. So this may be, for example, a sequence of numbers, like the first element is 1, the second element is 10, the third element is 20, and that's it. So this is the sequence. This is a finite sequence. The sequence may be infinite. For example, if we say that there are some other numbers, they're somehow defined. This will be an infinite sequence. As I have mentioned, a sequence is not equal to a set. So that's why some elements may appear more than once. So for example, we can say that the same element is appeared again infinitely using this pattern 110, 110, and so on and so forth. As mentioned, each element has an index. So 1 is the first element, 10 is the second, and so on and so forth. So order is very important. There may be various different sequences, for example, sequence of some shapes like square, triangle, other, again triangle, still valid sequence, why not? This may be a sequence of some functions, for example, cosine function of some number, there may be a sine function of some number, some other functions. This is still a valid sequence. Typically, we use natural numbers and like 1, 2, 3, and so on to represent positions in the sequence, like I have already mentioned. The first element, the second, the third, and so on. But other indexing schemes are also possible, so not limiting to natural numbers. So this is some idea or concept of a sequence. So now let's dive into what a numerical sequence is. A sequence in its broadest sense is any collection, any ordered collection of objects. It can be numbers, functions, and so on, as I have already mentioned. Our focus is on numerical sequence, specifically ordered collections of real numbers. Like, again, they consist of some numbers, which may be some fractions. This may be, again, some root. This may be root of another degree, whatever again, but these are real numbers. All these are not functions, shapes, and so on. So numerical sequences consist entirely of real numbers and often follow some rule or pattern. For example, there may be a sequence of, I will give a definition of a sequence a bit later, but there may be a sequence of fractions like this. For example, the first element when where n is equal to 1, it will be 1. The second one will be, 1, and so on and so forth. But if we say, for example, 2, the first element will be 1/2, the second element will be 1/4, 1/8, and so on and so forth. So again, numerical sequence. And mostly in calculus, the numerical sequences are used. So that's why sometimes if it is mentioned as sequence, by default, it's considered as a numerical sequence to avoid some misunderstandings. So now let's dive into the formal definition of a sequence. To understand sequences formally, let's recall our function definition from the video with the corresponding name. Just as a function maps one set to the other, as a reminder, function is something which maps from one set to the other. We can think of a sequence as a function mapping each natural number to a specific element. So sequence is again some mapping or a function which maps values from the natural numbers, which are denoted as n with this bold diagonal line, to a set of real numbers. And real numbers are defined as r with this bold vertical line. So this is the formal definition of a sequence. Again, mapping from natural number to a specific element. Just as a reminder, natural numbers are the numbers which we use for counting things like 1, 2, 3, 4, 5, and so on. 0 is an open question, sometimes considered as a real number, sometimes not. For us, it's not important right now. Real numbers are all the numbers like fractions, ratios, and so on and so forth. So basically the definition of a numerical sequence. Note on the notation. We say that sequence may be denoted as, for example, this. This is some common general element, and this is equal to the following definition. So if there is a sequence A1, A2, and so on and so forth, AN, so on, we can denote this in this format. So AN represents a specific term in the sequence and is referred to the nth term of the sequence. So this is the nth term of the sequence, where n is the order or the index. Pronunciation tip. We read AN as the following: A sub n. So sub means like index at the bottom. So A sub n, where n is the index, A sub n is the term. Let me clean the desk a bit and we'll proceed. All right. So the other way to define a sequence is using sets. So again, set is a collection of unique elements. So this may be element 1, element 2, element 3. So this is the end of the set. So the set may contain like different elements, completely different elements, whatever, but it cannot have any duplicates. And we can define a sequence using sets, using the following idea. So we say that each term is a pair of elements of the following shape, containing the index and the value itself. For example, this may be the following set. So the first element is 10, the second element is 100, the third element is 1000, for example. So you can see that we have defined a set which is a sequence. So basically we define the sequence using a set, using pairs of elements and using some values and their indices. Here xn is called the term or element of the sequence, and the notation xn signifies the nth term, as I have already mentioned. Important note on the completeness. A sequence is considered defined if there is a rule or method of determining each of its elements. So if you're not able to define some interesting formula, you have to define your set as a collection of all the elements. So for example, I don't know any pattern or any rule, any idea of how to represent the numbers, and that's why I have to depict all of them, because I don't know any idea of how to describe this as a formula. So this is my sequence, and I have to note all the values there. But there are some sequences which are easier to define using some patterns. For example, one classic example of a sequence is the sequence of the prime numbers. So these are the numbers greater than 1 with no divisors other than 1 and the number themselves. So this sequence, the sequence of the prime numbers, looks like the following. Oh, sorry, press something. All right. So this is 2, 3, 5, 7, and so on. This is an infinite set, and this is defined by the definition I gave you. So this is a sequence of the numbers which don't have other divisors except 1 and themselves. So 2 is divisible only by 1 and 2, 3 is divided only by 1 and 3, and so on and so forth. For example, the number 2 is divisible by 1, by 2, and by 4. So this is not a prime number, so that's why it's not considered as a part of this sequence. This sequence is ordered, it's infinite, it doesn't have any duplicates, so a perfect example of a sequence. And we don't have to write all these elements because we have some rule. It may be defined mathematically, it will be quite a long formula, but as an idea, you can give some formula to a person, to other person you are talking to, like find the numbers which have no other divisors except 1 and themselves. This will be a definition of a sequence. So here is the sequence of the prime numbers. Another interesting case of a sequence is a sequence of Fibonacci numbers. The interesting thing about this famous example is it is defined recursively. Again, the formal definition of a sequence requires us to give some formula or define a sequence so that every element may be defined easily. And for Fibonacci numbers, this is the following formula. So each Fibonacci number is just a summation of two previous numbers. The previous one and one before the previous. And it's important to know that there are two, like not default, but first numbers, f1 and f0, these are 0 and 1. So we can recursively calculate the others. So f2 will be f1 plus f0, which will be 1. f3 will be f2 plus f1. It will be 1 plus 1, it will be 2. So the Fibonacci numbers will be the following sequence. It will be 0, 1, 1, 2, 3, 5, 8, so on and so forth. Again, what we can say about the sequence, it's infinite. We can sum them up to the infinity and beyond, as always. All of them are ordered, so we have the first element, which is 0, we have the second, the third, and so on. So a perfect example of the Fibonacci, of the sequence. Interesting note, as I have already mentioned, they are defined recursively. So this definition is enough to say what each element with each index will look like. So we can easily say what will be the value of the 10th element, of the 100th, and so on and so forth. Another interesting case is the so-called Negafibonacci. So these are the numbers, the Fibonacci numbers, but to the opposite side, to the negative indexes. And this is a very interesting case because this is an example of a sequence which doesn't have to be indexed by the natural numbers. As a reminder, the natural numbers are the numbers like 1, 2, 3, which we use for counting objects in the real life. And the Negafibonacci are containing indexes of -1, -2, just negative integer numbers. There is a formula for defining them. I will just refer to the Wikipedia page. Here is the formula of defining any element with a negative index like -1, -2, and you can see that they look like that. So again, this is a sequence, Negafibonacci, ordered elements. They don't have to be more or less than the previous one. There is just a sequence with some dedicated indexes. So negative integers are also indices, and this is a great example of the case when the indexes are not natural numbers. So let's proceed and go to a very important comparison of the sequence with set and ordered set. We previously discussed sets in a function definition video, and a set is a collection of distinct or unique elements where order and duplicates do not matter. For example, again, a set may be a set of, this may be a set, and the set is defined again as unordered collection of elements. For example, this one is equal to 3, 10, 1, because the order doesn't matter. There will be no unique elements by definition of a set, which is not true for sequences. For example, if we say that there is some sequence may be defined as this one. It may contain duplicates, and it will not be equal to 3, 1, 1. So this is not true. Why? Because order matters. So this is an important comparison of set. This one is a set, while this one is a sequence. Another interesting entity or mathematical abstraction is an ordered set. We haven't mentioned this previously, but I will briefly introduce it. An ordered set is a set where the order does matter, but still duplicates are not allowed. So ordered set again may be defined using capital X, and we say that this one is not just a collection of distinct or unique elements, but this is an ordered collection of elements. But still, this is not equal to a sequence, because sequence may contain duplicates, ordered sets may not. Sometimes ordered sets, by the way, are defined using not curly brackets, but parentheses, so this may be mentioned as this construction. So structure, ordered structure is essential, but duplicates are not allowed. Last but not least, a very small but interesting portion of definitions are some operations which are allowed on numerical sequences. So let's assume that we have two numerical sequences. One will be xn. There will be some other sequence called yn, also containing some elements, and the same index n here means that they are of the same shape, so they may be infinite, they may be finite, but containing the same amount of elements. And we can define some operations on the sets. So let me show you several examples. We can multiply the whole sequence by a constant. So the following definition, C means constant. If we multiply the whole sequence by a constant C, we will have the following construction. So x1 will be multiplied by C, x2 will be multiplied by C, and so on and so forth. Xn will be multiplied by C, all the elements will be multiplied by C. So this is the multiplication of the sequence on some constant. We can also sum up sequences. So let me show you how this looks like. So if we want to sum up xn with yn, each element will be summed up with the corresponding one. The first one with the first one, the second, with the first one. The second one will be summed up with the second one. Again, so on and so forth until the end. They may be the same definition for the division and multiplication. An interesting one will be for the division, and of course you may probably have already guessed what may be wrong with the division, so I will give you the hint. This is related to the division by 0. So we can also define this construction. xn divided by yn, so sequence divided by sequence, and this is allowed only in case none of the yn is equal to 0. So none of them may be equal to 0, because in such a case some of the elements will be infinity. And this equals, this part is equal to, again, the element-wise division. So the first one is divided by the first one, so on and so forth. These are some basic arithmetic operations on sequences which are allowed, and they are quite frequently used. So, to conclude, today we covered the basics of sequences, particularly numerical sequences, discussing their definitions, examples, and different ways to represent them. In our next video, we'll explore bounded and unbounded sequences and analyze what it means for a sequence to grow infinitely large and small. Thank you very much for watching. See you in the next videos.